we will solve some more problems from the same chapter. We did attempt 35. No, we have to solve number 35. The non-zero elements of Z3I now. Non-zero elements here form a multiplicative group of order 8. An abelian group of order 8 under multiplication. We will check on that, and then we want to find what is it isomorphic with. Because it is group of order 8 and abelian, it must be one of these, either a cyclic group of order 8 or a direct sum of Z4 and Z2, that is a group of order 4 and a group of order 2, or Z2 plus Z2 plus Z2. That again is of order 8. So let us find out what happens in the case Z3I. There are elements. How many elements are there? A plus Bi, where A and B are in Z3. So 3 possibilities for A, 3 possibilities for B, altogether 9 elements. So if this is equal to R, now R star is equal to R minus the element 0. So there are 8 elements, R star as order 8. So first of all, under multiplication it is a group. So it will be in fact a field, non-zero elements forming a multiplicative group. Let us just check on that. What are the elements? There are only far too many. 0, 1, 2, then I, 2I, adding I to this and 2I, then 1 plus I, 1 plus 2I, and 2 plus I and 2 plus 2I. Oh, far too many elements. I don't want to construct the multiplication table 8 by 8. But we still can prove that this is an abelian group under multiplication if I can check that R star is the group of units. That is, there are no zero divisors. If I prove that, then I am through, because I know that a non-zero element here will be either a zero divisor or a unit. So let us check. A1 plus IB1 is a zero divisor if there is another element A2 plus IB2 which annihilates it. And we will of course assume that A1, B1 not equal to 0, and so A2, B2 also not equal to 0. And this as usual gives us A2 upon A1 is equal to minus B2 upon B1 is equal to T. And what do you have? So when you substitute here A1, this equation reduces to A1 plus IB1 into A1 minus IB1 is equal to 0. So what does that give us? It gives us that A1 square plus B1 square is equal to 0. Now where are A and B, A1 and B1 are in Z3. I don't have to look at all these elements, but I can certainly examine the elements in Z3. What is Z3? Z3 is just 0, 1 and 2. That is simple enough. So what are the squares? Squares are 0, 1 and 1. So can I possibly have a solution for this where A1 and B1 are not 0? No, I can't. Because each square, non-zero square is 1 and the addition will simply not be 0. So A1 square plus B1 square equal to 0 has no solution, which is not equal to 0, 0. Therefore, every non-zero element in our R is a unit, and I know that the set of units forms a multiplicative group. So U of R is equal to R star, and it is a group under multiplication. So I have achieved the first part. Now I need to find the structure of this group of units and find out whether it is like Z8, that is it is a cyclic group of order 8, or it is Z4 plus Z2 or Z2 plus Z2 plus Z2. I have already written down all the elements there. So I can check the order of different elements and find out what is happening. Order of 1 is 1, order of 2 is also 1, order of I is 4. Order of 2i will also not give me anything good, because 2i square is I square, that is minus 1, so that order will also be 4. Let us look at the order of 1 plus I. 1 plus I square, what do I get? 2i, that is because 1 minus I is 2i. And then 1 plus I cube, what is that? 1 plus I cube is I multiply 2i by again 1 plus I, so that will be minus 2 is plus 1 plus 2i, and 1 plus I. 4, that is important, because if the order is 4, then I will have to have the biggest order to be 4, but let us see. If I multiply this by 1 plus I, what do I get? 1 plus 2 is 3 is 0. The real part is 1 minus 2. So it is minus 1, so that is 2 in fact. Right? 1 plus 2i square is 1 minus 2, that is, and then I, coefficient of I is 1 plus 2i, that is 0. So this is 2. So 1 plus I raised to 4 is not 2. So the order of 1 plus I is not 2 and not 4. So the only choice is that I know now that 1 plus I will have order 8, and I know it will generate the whole group of units. Let us just check. Fourth order gives me 2. Fifth order, I don't really have to check, because from the elementary group theory I know now that the order is going to be 8. These 5 will be 2 plus 2i. And 6 power will be 2 minus 2, so that goes to 0, and the I coefficient is 2 plus 2 is 4, that is I. And 1 plus I raised to 7 will be the remaining, which is not covered yet. First order is just 1 plus I. What is not covered? Let us check. It is I minus 1, so it is 2 plus I. Yeah, that was not covered so far. And 1 plus I raised to 8 has to be equal to 1. It has no choice. Therefore, the group of units now I know is a cyclic group of order 8. So that completely determines what the ring Z3I is. So this one was 35. Let us look at 36, which is the generalization of the same problem. Instead of Z3I now, we are going to look at Zni. So the general element will be with A and B in Zn. Okay. I square is minus 1. I don't have to write that every time. For some prime P, Zpi is a field, and for others, for some primes Zpi is a field and for others it is not. So what is it? Replace n by p when n is equal to p. Oh, it should be polynomial ring. So it is the square bracket. This is a field, and for some p the same ring is not a field. We have already seen that for p equal to 5, this is not a field because we have got some divisor of 0. This is not a field, but Z3I is a field. Because just now we proved that all non-zero elements are in fact units and they also form a cyclic group. So what is the condition? So the condition is that Zpi may or may not have divisors of 0. We have learnt enough of the divisors of 0. We know that for a finite integral domain, every non-zero element is either a divisor of 0 or a unit. And if there are no divisors of 0, then that finite integral domain is a field. Otherwise it is just a ring. It is not an integral domain if there are divisors of 0. So let us check the condition. If Zni has divisors of 0, then Zni is not an integral domain and therefore not a field. If Zni has no divisors of 0, then Zni is an integral domain, and because it is finite, it is also a field. So let us check again when it is an integral domain and when it is not. So consider a1 plus ib1 with a1 b1 not equal to 0 to be annihilated by another element a2 plus ib2 is equal to 0. Then the usual things are obtained. This is equal to some t, and this reduces to t into a1 plus ib1 into a2 minus ib2 is equal to 0, or this is a1 and b1 again, or a1 square plus b1 square is equal to 0. So what is the crux? The main thing is this. If this equation has a solution, non-zero solution, then our ring is not an integral domain. So, if a1 square plus b1 square is equal to 0 has non-zero solution in Zn I, then Zn I is not integral domain. If such a solution does not exist, then there are no divisors of 0. So, the same ring Zn I is an integral domain and also a field because it is finite. Okay? So, you will realize that this equation a square plus b square equal to 0 having a solution is an important property, and for some primes solution exists, for some it does not exist, and then you will learn if you study some elementary number theory that if P is congruent to 1 mod 4, then the solution exists. And if P is congruent to 3 mod 4, then the solution does not exist. N, oh, that is n is equal to P. Oh, n is equal to P. Yes, I am sorry. We are considering n to be equal to P everywhere. So that settles our problem 36. Show that a finite commutative ring with no zero divisors has a unity. That is the next problem. Problem number 37, and that also uses a trick we have used before. If you have a finite set, you can always enumerate it. You can actually write it down as a finite set, and then that is the trick. What do we want to show? A finite commutative ring commutative ring with no divisors of 0. Has unity. So, unity does exist. But the condition is that there are no divisors of 0. As I said, we just enumerate all the elements. Let R be equal to 0 is there, of course, because it is abelian group under addition. So, 0 is the identity in that abelian group, and then the elements I can write as A1, A2, An, where the order of R is n plus 1. Since the order of R is finite, commutative ring, so I can write the elements like this. What do I do next? All these elements are non-zero. So, what I do is consider A into R. So, enumerate again. What are the elements? 0. A1 square A1, A2, A1, A3, dot, 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 finally A1, An. So the elements again are n plus 1. So what do we have? These are all the same elements as these because there are no divisors of 0. There exists no divisors of 0. So first we have to check that these elements are exactly the same as this. If not, two elements here will be the same and then A1 will be a divisor of 0. First, A1 square, A1, A2, A1, An are all different. Else, A1 is a 0 divisor. And these are n in number, these are also different n elements. So, set theoretically A1 square, A1, A2, A1, An, this is the same set as A1, A2, An. Okay? So, now what do we have? So, this A1 must appear here as well. Therefore, there exists K such that A1 is equal to A1 AK. Okay? This K is somewhere here. K can be 1, 2, 3 up to n, such that A1 AK is nothing but A1 itself. We will show that this AK in fact is the identity for this ring. How do we show it now? I want to check that for any other element A2, A3, AK works as a multiplicative identity. That's not difficult. That's not difficult. Why? Because consider any A2, AK or let me just do it more generally. Now consider J bigger than 1. So this J is somewhere here. Again, this J must appear here. Okay. H equal to A1 into AR for some R. Okay. But I know that A1 is A1 AK. So this is equal to A1 AK AR and the ring is commutative. So let me go over there so that you can see better. What have we got there? AJ, J greater than 1. AJ is also equal to A1 into AR for some R. And this is equal to A1 AK AR. The ring is commutative. So this is A1 AR into AK. A1 AR is still AJ. So what have we got? For any other J bigger than 1, AJ is equal to AJ AK. What does this mean? This implies that AK is the multiplicative identity. we have found the multiplicative identity and R has that identity. Well, problem number 38 is too easy. I am not going to try that. You should be able to do it very quickly. Let us look at 39. What does that say now? R is a commutative ring without zero divisors. Commutative ring and no zero divisors. We are looking at 39, right? Yes. Show that all the non-zero elements have the same additive order. Have the same additive order. What does that mean? In the additive group, the order is given in the additive group. A has got additive order n, means a plus a n times, or n a is equal to 0. So what do we have now? A commutative ring, no zero divisors. So, in other words, if A and B are not 0, then NA equal to 0 implies, we want to prove this, that NB is also equal to 0. See, if A has additive order n, then NA is equal to 0. In the additive group, this is the meaning of the order. So, if we show that NA equal to 0 implies NB equal to 0, then we are through. How do we go about that? Suppose NA is equal to 0, then A plus A plus A n times this is equal to 0. Multiply it by B, then what do you get? AB plus AB, this is just rearranging our data. This is equal to 0. Now use the distributive law, and what do you get? A, use it on the other side, into NB is equal to 0. If you take the A out and collect the B's inside, this is equal to 0. A is not equal to 0, and there are no zero divisors. So, this implies that NB is equal to 0. So, the additive order for non-zero elements is the same. This was 39. Okay, suppose that R is a commutative ring. I am reading the next one. Without zero divisors, show that the characteristic is 0 or prime. Oh, that you should do very easily, because NA equal to 0, and if N is composite equal to R into S, then okay, I'll indicate how you do it. I think I have done it once, but I'll just indicate the proof, but I will not give the details. You should very easily supply them. If use this fact also, if N is equal to R and S, R is both bigger than 1, that is a proper factorization of n, and Na is equal to 0 under the same conditions, then R into S into A is equal to 0. Therefore, either Ra equal to 0 or Sa equal to 0. If Ra not equal to 0, then R times S times Ra is equal to 0. So, this, just rearrange the terms and this is what you get. Okay, the next one is 41, is any finite field, it has to be of order p raised to n, it cannot have order n where two different primes divide n. We have done elementary problems which will lead to here, lead to this problem. So, I can actually leave it for you to do it. If there are two different primes dividing n, then we will not get the non-zero elements to be a field. Let us look at 42. We have done enough material to solve this problem. Let us check 42. Now this is 245. Maybe I will go back to 41 a little later, because that requires you to use your finite abelian group theory as well. We will come back to it. Okay. Let us look at 42. Now we are in an integral domain of prime characteristic. R is an integral domain and characteristic of R is equal to P, a prime, it is not 0, A. Now these are very basic facts and you will be using them again and again if you study field theory. B, we have to show these things. For all positive integers, x plus y raised to p raised to n is equal to x raised to p raised to n plus y raised to p raised to n. Obviously, B follows immediately from A by raising to power p both the sides. The last one is find elements x and y. Where are they? In ring of characteristic 4, such that this equation is not satisfied. That is, x4 plus y4 is not equal to x plus y bracket 4. Let us solve this. That is, so what is x plus y raised to p? Again, you have to use your old friend binomial theorem and just expand. What is this? X raised to p plus pc1 x raised to p minus 1 into y. Pc2 x raised to p minus 2 y square plus finally y raised to p. Now look at all the coefficients here, Pc1, Pc2 etc., and finally here it will be Pc p minus 1, which is same as Pc1. Now each Pci here is congruent to 0 mod p. P divides each of these coefficients. Therefore, since the characteristic is 0, all these terms just vanish. Therefore, x plus y raised to p is equal to x raised to p plus y raised to p. Characteristic is p implies that every coefficient is 0 because it is divisible by p. And repeated application of A gives B. This gives B. You just raise to power P both the sides again and again R times or N times. Let us look at C. A ring of characteristic 4. So, what do we take the ring as? Z4, 0 bar, 1 bar, 2 bar, 3 bar. We want fourth powers now. So, what are the fourth powers? Fourth powers are 0, 1, fourth power of 2, 2 raised to 4 is 16, that is 0. And 3 raised to 4, 81, that is 1 again. So, these are the fourth powers. So, we need an example where x raised to 4 plus y raised to 4 is not x plus y raised to 4. Can I have these two? X raised to 4 plus y raised to 4 is not x plus y raised to 4. Yes, because x equal to 1 and y equal to 2, then x plus y raised to 4 will be equal to 1, and okay, this doesn't work. I mean, this satisfies the law. This satisfies what we want. So, this is not good for us. Then what do we take? Shall we take 1 and 3? Yes. X as 1 bar and y as 3 bar. Then x plus y, that itself is 0. So, that raised to 4 is 0. But what is x raised to 4 and y raised to 4? That is 1 bar plus 1 bar is equal to 2 bar, and that is certainly not 0 bar in Z4. So, we have got an example where this rule x raised to n plus y raised to n is equal to x plus y raised to n is not satisfied. N is the characteristic. But then the difference is that this n is not a prime. Therefore, Zn is not a field. Lot of things matter if n is a prime or not. Okay, let us go back to this 41. I said you can do it, you can certainly do that, but there are a few more things which have to be considered. F is a finite field. I will only indicate, but you will have to revise your theory of groups here. If the order of F is equal to n, where P1 and P2 both divide n, two different primes, and P1 not equal to P2 of course, then you are going to run into trouble. You cannot have it this way. Why? Because F is an abelian, finite abelian group, finite abelian group under addition. So, by the fundamental theorem on the structure of this group, it will be direct sum of cyclic groups. And P1 and P2 will divide those subgroups. And P1 and P2 being two different primes, that is going to give you problems with the characteristic of the field. F is a finite field, so the characteristic has to be a prime. Which prime will it be, P1 or P2? If there are two different primes dividing n, then there will be two different primes dividing those factor groups, and that will give you trouble. So, you have to look up the theory of finite abelian groups and the structure, and then apply what we have learned, and you will be able to show that this is not possible. You will run into contradiction if two different primes divide n. Okay? I want you to try it now on your own. Let us go to problem 43. Let R be an integral domain with unity. Of course, if it is an integral domain, it has to have unity, 1, and non-zero characteristic. And characteristic of R is equal to some prime P. If A is nilpotent, A in R is nilpotent, show that there is a positive integer k such that 1 plus a raised to k is equal to unity. I have a little problem with this problem. If R is an integral domain, it will not have zero divisors. How can A be a nilpotent? Seems to be a little problem there. Should consult that. And nilpotent element is one which raised to some positive power will give you 0. But R is integral domain, so it is not supposed to have divisors of 0. It should not have divisors. Okay. Let us just forget about that integral domain business. Let me read the problem again. R is an integral domain with unity and non-zero characteristic. If A in R is nilpotent, prove that there is a positive integer k such that 1 plus a raised to k is equal to 1. What you need to do here is just expand this. A is nilpotent implies that a raised to n is equal to 0 for some n. And if you expand, if k is large enough, and all you have to do is use the binomial theorem, and then what do you get? Kc1 into a plus Kc2 into a square, and then how long do you have to go? Kcn minus 1 only, because the rest of the terms are going to be 0. So to get all these terms to be 0, you want this product, this power to be equal to 1. You need all these coefficients to be 0. So what you need to do is k equal to n or k is equal to n some power of p which is greater than n. Then you can show that all these coefficients are divisible by p and therefore they reduce to 0. But according to me, there is a problem with this problem because you simply cannot have a nilpotent element in an integral domain. If it is just a ring, well, maybe. Okay. Number 44 is give an example of an infinite integral domain that has characteristic 3. So far we have considered integral domains or rings constructed out of Z2, Z3, Z5 which were finite, because we considered things like Z3i, Z5i. So the final ring which was generated by Z3 and I, Z5 and I, they were all finite. So in this problem we want an infinite integral domain. 44. What do you think? What are the infinite integral domains that you have already seen? Infinite integral domain with characteristic 3. Now, which are the infinite integral domains that you have seen so far? Z, yes, Q, R, C, is that all? Some more. Think. What about the polynomials? Zx, Qx, are they not integral domains too? They are. They are also integral domains. And they are generated over Z in the polynomials in the indeterminate x. What can be the degree of the polynomial? Any positive integer. How many positive integers? Infinite. So, if I say that I look at this, polynomials in x with coefficients in Z3, mind you Z3 is a field. Now, Z3 is an integral domain, so this is also an integral domain. You can check that there will not be divisors of 0 in this ring also. So, when you are thinking of rings, don't just stop at 2Z or 3Z or ZP, Zn and these, but also think of polynomials and also of matrices. In some problems, you will need to look at matrices because when you want a non-commutative ring, matrices usually help you. Okay, so let us go ahead. Oh yes, right in the next problem, we are coming across the matrices. Problem number 45. What is that? Let R be a ring and M2R. So what is M2R? In our notation, 2 by 2 matrices with elements in R. These two have the same characteristic. What does it mean? We need to explain that characteristic of R is the same thing as the characteristic of M2R. Easy, because what is M2R? M2R is equal to matrices A, B, C, D with A, B, C, D in R. If the characteristic of R is non-zero, okay, if characteristic of R is equal to P, say, then P into A is equal to P into B is equal to P into C equal to P into D is equal to 0. Therefore, characteristic of M2R is also equal to P. Because if you add the matrix to itself P times, then it will be 0. If characteristic of R is equal to 0, then you can similarly show that the characteristic of M2R is also 0. If this, then for some A, NA is not equal to 0 for all N. There will be an A there. What are the conditions now? R is just a ring, doesn't matter. Therefore, if I take the matrix, just see, I can have either A or 0 at some places, is such, I call it capital A, that NA is not equal to 0. Because the addition is component wise, and if A plus A n times is 0, that happens if and only if NA is equal to 0, NB is equal to 0, NC is equal to 0, and ND is also equal to 0. So that was not difficult. So the characteristic is maintained. Shall we look at 46? That's easy, I think. R is a ring with M elements. Show that the characteristic of R divides M. I am not going to do this problem. Just look at your group theory and remember that R is an additive group. Next one, explain why a finite ring must have a non-zero characteristic. That is also easy, because if the characteristic is not non-zero, then there will be an element which added to itself n number of times gives all different elements. So there will be infinite members, infinite elements in the ring. So that is rather easy. Okay, let us look at 48. That is rather instructive because it is a little contrary to our normal understanding of the numbers as you studied in the school. What is that? Number 48. Find the solutions of x square minus x plus 2 equal to 0 over Z3i. Look at this quadratic and you know that this has no solutions in real numbers. Does it? No. It doesn't have solutions in the real numbers, because if you look at your old theory that b squared minus 4ac or h squared minus ab, whichever notation you are using, that is going to be negative and the roots are going to be complex. But no real root doesn't mean there is no root in Z3i. What are the members of Z3i again? 1, 2, I, 2 plus I, 1 plus 2i, 2 plus 2i. Have I got them all? 8? No, I got only 6, so which are missing? 1 plus I. What is missing now? 1, 2, 3, 4, 5, 6, 7. Something is missing. Only 0, 0 is not allowed, but okay. 0 plus I, 1 plus I, 2 plus I. Yes, 0 plus I, 1 plus I, 2 plus I. Then 1 plus 2I, 2I is missing. 0 plus 2. So that makes it all 8. So what do you want? You want the solutions of x square minus x plus 2 is equal to 0, or in other words you want the solutions of x square minus x is equal to 1. It is the same in Z3i. So x square minus x is equal to 1 is what you want to solve. So for that you need to consider all these squares and or look at the table, make the table. I think the table is given in the book on page 239, and all you need to do is you look at x square minus x and see when that happens to be 1. You will find two solutions. X square minus x has to be 1. So 2 plus I is one solution. X 2 plus I, see 2 plus I square. Two plus I square is given as I. So this minus 2 plus I will be minus 2 and it will be 1. So this works. And the other solution that you will have is 1 plus 2i. Will it be 1 plus, yes. 1 plus 2i square is I. No. There are two solutions. Is it 2 plus 2i? Yes. 2 plus 2i square, yes. 2 plus 2i square is equal to 2i. So you subtract 2 plus 2i, you get 1. You subtract 2 plus I, again you get 1. So these are the two solutions, 2 plus I and 2 plus 2i. So contrary to what you know about the field of real numbers, this equation does have solutions in this field, Z3i. Okay, we will meet again later, but now we will move on to the next topic when we meet in the next lecture. Goodbye.